Good morning. This is going to be a video about the Robinson annulation. And annulation here is going to basically mean making a ring. And the general setup for this is that you need a conjugated carbonyl compound, and it has to have an alpha carbon on the opposite side of the conjugated system that has at least two hydrogen atoms on there. So there could be another group here, but no more than that. So this is kind of the simplest setup. And then you need another carbonyl compound, and it has to at least have an alpha methyl, or at least one alpha carbon. And then it could be an aldehyde, or it could be a ketone. So there could be some other group here. So the absolutely required parts here, I'm going to change to be in red. So you have to have these parts. Okay, I'm going to show you sort of the overview of what happens and how I tend to draw it. So this is how I always set it up. So if the compounds are given in another orientation, I always rotate them and set them up this way because this is how I remember it. Another way might work for you. But in the end, what's going to happen is this alpha carbon will end up bonded to the conjugated system because the first step in the Robinson annulation is a Michael addition. Okay, so if we deprotonate this alpha carbon here, that's going to be a a good nucleophile, but not a very strong nucleophile. So remember that the strong but not very strong nucleophiles are going to do the Michael addition. So we're going to end up with a new bond here. Now, as part of that process, of course, this double bond here just becomes a single bond. So I'm going to kind of color that in to make it a single bond. And then the other thing that ends up happening, so once that happens, then this alpha carbon is going to attack the carbonyl carbon here in basically an aldol addition. Okay, so this carbon and that carbon are going to end up bonded together. And in the end, what's going to happen is this oxygen is going to get protonated twice, and it's going to leave as water. And you're going to end up with a double bond here, because after the aldol addition, there will be a condensation step. Excuse me. Okay, so let's actually go through the mechanism. So I'm just going to use the setup that I've drawn here. And it's going to be sodium hydroxide. And then there's going to be heat. Okay. And it might be, I think what you tend to do with these is you tend to let them stir for a while at lower temperatures to do the Michael addition and to do the aldol addition, and then you heat it up so that it can do the condensation step. So first step is going to be the sodium hydroxide will deprotonate the alpha carbon of the carbonyl that isn't a conjugated carbonyl. Okay, so we know this setup, so we're going to end up with the enolate anion. And we remember the reason that this happens is, of course, because we have resonance here. That's why we end up with a pK of 19 here. Because we can do this, okay? But this is going to be my nucleophile, and that's going to attack the conjugated carbonyl. So this will attack here. Electrons go here. Oops, left off a methyl. That's not good. Okay, so now I have a bond here, and I have a lone pair here. Now, we can draw the other resonance structure, which of course is going to be the more stable of the two. However, in the end, what's going to happen is this carbon's going to get protonated. Notice that we did just make water, and we do probably also have at least some water present with sodium hydroxide. That's typically going to be an aqueous solution. And so water is going to act as our acid here, since we're in a basic environment. And since we're in a basic environment, it's okay for our intermediates to have negative charges. Okay, so now we have this, and so we see now that we've tethered the two molecules together, and now we're ready to do our aldol condensation. So the hydroxide, I suppose I should draw it out. The hydroxide will deprotonate this alpha carbon, and then we will end up with this. And of course, this is ready to attack. So this is going to attack the carbonyl there. And we'll go to the next slide. We now have made the ring at this point. So, of course, we need to protonate that oxygen. And we are again assuming we have plenty of water present here. Okay, and notice this is our beta hydroxy carbonyl, which is what we get with a aldol. This is basically the aldol product. And so you can recognize these because we have a carbonyl carbon here, we have the alpha carbon here, and we have the beta carbon here. And we have that hydroxyl group is at the beta position. Okay, so we've now completed our aldol reaction. Next, we need to do our condensation step. So again, we are in a basic environment, and this hydrogen atom, or these hydrogen atoms here, are still going to be relatively acidic. And so we're going to be able to take off one of those protons with the hydroxide. And you may be wondering, wait a minute, aren't we going to deprotonate the OH group? And you're right, that could happen as well, but that doesn't really get us anywhere interesting mechanistically speaking or reaction-wise. So that probably is also happening. And these two probably have kind of similar pKa's because terbutyl alcohol's pKa is 19. But however, this has the resonance going on, and also now you've got an additional electron withdrawing group with that hydroxyl next door. So that's going to increase the reactivity here. One thing I just realized is I wasn't labeling my steps. So let me go back and do that. So this, of course, was a proton transfer. This is going to be the Michael addition step. Okay. And then this is going to be the proton transfer. This is another proton transfer. And then this step is going to be the nucleophilic addition. This step, of course, is just another proton transfer. Another proton transfer. So there's a lot of proton transfers happening in these mechanisms in general. All right, so now we have deprotonated at the new alpha position, basically, or at the alpha position there. And this would be more acidic. The position here on the left would be more acidic than the one on the right because of that hydroxyl group being present. Okay, so now we have a negative charge here, and we have our OH here. And now we are ready to do our E1CB mechanism. All right, and the E1CB stands for unimolecular elimination conjugate base. Okay, so this is a very different mechanism than our other two elimination mechanisms, because basically we're taking the proton off first, and then the leaving group leaves and the pi bond gets made together, right? So it's because we're in this very unique environment with this unique substrate. So the step in the E1CB is that this lone pair will go and make the pi bond, and then the hydroxide kind of gets ejected out. And that's a reasonable leaving group in this environment because we know we have lots of sodium hydroxide present. So that's an okay leaving group here, whereas normally it would not be an okay leaving group. So we have made the pi bond here on the left. Notice that the new alkene is kind of opposite where the old alkene was when we're making the new ring. And we, not all together, but effectively, water kind of left here. It's just that it left in two separate parts, right? We've got the hydroxide that left and the proton that got taken in this step here. So that is the Robinson annulation. Again, going back up here, the way, this is obviously a very long and complicated mechanism. So you're unlikely to get a question that asks you to go through the entire mechanism of this. You're much more likely to get little bits and pieces of it, or maybe, just asked to figure out either, here's the product of the Robinson annulation, what were the reactants, or here's the reactants of the Robinson annulation, draw the product. And so that's where knowing how the bonds end up. So knowing that the regular carbonyl alpha carbon is going to get bonded to the conjugated carbon, the 4 position basically, if you will, because of the Michael addition. And then the other alpha carbon on the conjugated carbonyl, or the formerly conjugated carbonyl at this point, ends up double bonded to the carbonyl on the non-conjugated carbonyl. All right, and then of course that oxygen leaves as water. And then that will allow you to, kind of see the product and draw it correctly. And, just don't forget these side groups and make sure, sometimes there's something attached here, so you'd want to make sure that ends up attached here. And sometimes there's other things coming off here. Sorry. So you'd want to not forget those other parts and carry those along with you. So that's the Robinson annulation.